Hi everyone, I'm Adam Geller. I'm a PhD student at the University of British Columbia.
Hello, I'm Justin Frank. I am a research assistant at the University of British Columbia.
Today we're going to be talking about modeling the WebAssembly language in Redex. And this is part of an ongoing research project at the University of British Columbia that we've been working on along with William Bowman, who I believe will also be giving a talk later that you all should go and check out. WebAssembly, or WASM, is a stack-based assembly language that is meant to run in the browser alongside JavaScript for performance-critical applications. It is meant to be fast and safe. WebAssembly is also very nice because it is one of the few commercial languages to be released along with a formal language specification. A formal language specification describes precisely what programs can be written in a language and how they will behave. For example, here is the syntax, or a snippet of the syntax of WebAssembly. And we can see that there are a number of different instructions here, such as integer binary operations, which can be things like addition, subtraction, multiplication, and other sorts of operations on numerical values. We also have some control flow instructions, such as ifs and branching and function calls and returns. As part of our research project, we want to be able to quickly and easily experiment with making changes to the WebAssembly language. And to do this, we want a machine model of WebAssembly. That is, a model that can be executed on a computer. And to build such a model, we've used Redex. Redex is a domain-specific language embedded in Racket that is meant to be used to create machine models of languages. Here is our Redex model, and specifically this is the model of the WebAssembly syntax written in Redex. And it looks very similar to the WebAssembly model. However, there are a few differences, such as the use of S expressions, because this is written in Racket. But we still have binary operations on integer values, which can be things like add or subtract. We still have control flow operators like ifs and branches and calls and return. One interesting thing to note is that both in the formal specification and in the Redex specification, because WebAssembly is a stack-based language, instructions do not take explicit arguments, but rather take implicit arguments from the stack. For example, here's the reduction rule for binary operation. A reduction rule is a particular way of describing how a program will behave. What a reduction rule does is it basically maps programs in one state to programs in another state, taking one step at a time. So in this rule, we have a binary operation and then two values on the stack, C1 and C2. And after we execute this instruction, then we just have one value on the stack, C. And C is the result of evaluating the binary operation on C1 and C2. And this looks very similar to the rule for the binary operation in the formal WebAssembly semantics written on paper. The one difference is that whereas in the formal semantics, they have this type of implicit decomposition, we have to do this explicit decomposition. And by decomposition, I mean pulling apart the program to figure out what the next instruction to execute is. And that's what this in-whole construct provided by Redex is doing. It's just picking apart the program and looking for the next instruction to execute. And when we say if it's a binary operation, we execute a binary operation. And we have this useful eval binary operation meta function. A meta function in Redex allows us to declaratively define a function outside of a reduction relation. So here we use this meta function to pattern match on the binary operation and actually escape into Racket to compute the value that should result from applying the binary operation to the two inputs, C1 and C2. Another interesting rule to look at is the rule for grow memory. The reason why grow memory is interesting as an instruction is because it can step to two different program states, depending on whether it succeeds or fails. And this is similar to, for instance, trying to open a file. You don't know whether it's going to succeed or fail. So we can use Redex's helpful stepper function to see a GUI that will show us how our program will be reduced. So if we start with a program which has the values 1 and 2 on the stack, and then the next instruction is to add those values together, we wind up with the value 3 on the stack after one step. However, if we instead look at the reduction of grow memory using this stepper GUI, then we see that there are two resulting program states. One where the instruction failed and we have a result -1 and the memory hasn't changed. And the second result where the memory has been grown and the result is 1 to indicate success. The semantics of WebAssembly rely on extra syntax introduced to keep track of runtime information, such as the state of the current story, which S here, which stores information about functions, table, and memory in WebAssembly. We also have some additional instructions for use at runtime, such as trap, which represents a runtime error. In Redex, we can easily define languages using the define extended language construct, which allows us to add additional syntactic forms and extend existing syntactic forms, as we see here for instructions. Additionally, using Redex, we can easily write tests for the semantics of a language. For example, here is a simple test saying that if we have a program with the values 1 and 2 on the stack, and then invoke the addition instruction, we should result in a program state with the value 3 on the stack. This test arrow E function from Redex basically says, is there a way, starting at this program state, to reduce the program so that you reach the ending program state? And for this is a very simple test, so this is obviously true for the binary operation. If we look at the test for grow memory, we see that we have two tests with identical input, but different final states, and that's because of the non-determinism of the grow memory rule. I will now pass it over to Justin to talk about validation.
Another one of the special properties of WebAssembly is that it is memory safe, which is an important property for a language that is meant to run in web browsers. You don't want to visit a web page that can corrupt its host environment and perform arbitrary code execution and steal secrets from your computer. WebAssembly ensures memory safety through a set of validation rules. And for anyone who is not familiar with this syntax, they're presented as premises above a horizontal bar above a conclusion, where knowing all the premises get you the conclusion. And the conclusion for this typing judgment is of the form under a context C, which will include things like types of the functions. The instruction tconst C has type and then nothing to 1t, where the things on the left of the arrow are the types of the values that are getting consumed off of the stack by the instruction, and the types on the right of the arrow are the types of the values getting produced by the instruction. So as you can see with the binop instruction, it is pretty similar, except that the types getting consumed, except there are two of the types getting consumed and one getting produced. And these typing rules for WebAssembly ensure that you never try and, say, add a 32-bit floating point number to a 64-bit integer, or you never call a function with the wrong number of arguments or with the wrong type of arguments, so that the instructions never, load or write a wrong value to the stack. And if we scroll down here to things like the block instruction, we can see a typing rule with premises. So it says that if the block is annotated with the type T1 to T2, and the instructions inside the block have a derivation that gives them the type T1 to T2 with this extra thing added to the context, then we can say that the block is valid and has type T1 to T2. So one of the nice things about Redex is it allows us to encode these judgments basically as you see them here. So you can see that looking at the constant rule, for example, that this line in Redex is basically the same as this line in the specification, with some minor syntactic changes. And even if we go down to the more complex rules, they aren't that far off of how they are written down in the specification. Redex is able to automatically check derivation trees made from these judgments, as you can see here. Here is a test that checks that a derivation for this instruction sequence that is adding two 32-bit integers together is valid. As you can see, this is quite verbose, and we'd like to not have to write out these derivation trees by hand. We'd like to be able to automatically generate them. Redex does actually provide this functionality but not for our judgments. Redex can do this if you can write the derivation in such a way that each operand is either an input or an output to the judgment. So writing down the judgment is also writing down an algorithm for finding derivations. And unfortunately, the WebAssembly type system cannot be expressed in such a way. However, you can write programs in Racket that generate these derivation trees, as we have done here, and then use Redex to check whether the derivations generated by this algorithm are valid. And so now we can test a lot of the type system, the typing rules, and the type checking algorithm or derivation finding algorithm at the same time. So another useful thing that Redex allows you to do is to extend these judgment forms. So say you're working on an extension to WebAssembly, or you want to model an extension to WebAssembly that adds some new instructions that might introduce some novel features. To add typing rules for those instructions, you could define an extended judgment form, extending this judgment here with rules to type your new expression. So the Redex model is publicly available and hosted on github.com/atgeller/wasmredex. The current version of the model only covers the 2017 PLDI paper version, but we are working on updating it to catch up to newer versions of the WebAssembly language. Thank you for your time.